Hi everyone and welcome to the Learning Curve. In this video, I'll be focusing on the applications of the rules of probability, including the general probability rule, conditional probability, the joint probability, and marginal probability. Let's get into it. Here we are told that the probability that a randomly selected patient is rheumatic is 0.35. The probability that a randomly selected patient suffers from depression is 0.19. And the probability that a patient is both rheumatic and depressed is 0.06. We are asked to find the probability that A, a randomly selected patient is depressed or rheumatic. Symbolically, we're going to use D as a legend for depressed and R as a legend for rheumatic throughout the problem. So always nice to establish a legend, which could be just a letter that commences the words or the events for which we're calculating the probability. So here we're asked, again, to calculate the probability that a randomly selected patient will either be depressed or rheumatic. When we are calculating the probability of either one outcome or another, then we use the general probability rule. And the general probability rule using these symbols would be the probability of D union R. That is the probability that someone is depressed or rheumatic. The union here means or, is equal to the probability that a person is depressed, D, plus the probability that a person is rheumatic, R. And we're going to subtract the probability that a person is depressed and rheumatic. That's the intersection of the two events. So simply, we're now going to substitute the information that we have from the problem. This is called the general probability rule. So the probability that a person is depressed is given to us as 0.19, 0.19, right there. Yes, 0.19. And the probability that a person suffers from rheumatism is given to us in the question as 0.35 there. And the probability that a person is both depressed and suffers from rheumatism is given to us as 0.06. That's the intersection of the two events. So that's 0.06. So what we're going to do here is that we're going to add the two probabilities, 0.19 plus 0.35, which gives us 0.54. And then we subtract 0.06, which gives us 0.48 or 48%. So if a person is selected at random from this data set, there's a 48% chance that they will either be depressed or rheumatic. 48% chance. Second question then asks us, if a student is selected at random, what is the probability? So the students here are, the patients here are students. So if a patient is selected at random, what is the probability that they are neither depressed nor rheumatic? So essentially what we're calculating here is the probability of D union R all complement. The complement of the union is what we calculate when we're asked for the probability of neither one nor another event. So here we're asked to calculate the probability that a randomly selected patient is neither depressed nor rheumatic. So that is just the complement of D union R. And to find the complement of the union, we take 1, which is the total probability, minus the probability of the union itself. So this will be 1 minus the probability of D union R. This is how we always find the probability of neither nor. We first need to know the probability of the union itself, which is either or, and then subtracting the probability of either or from the total probability of 1 gives us the remaining space of neither nor. So this will be 1 minus 0.48, because we found D union R here to be 0.48, and that is going to give us 0.52 or 52%. So what this is saying to us is that there's a 52% chance that a person selected at random from this data set will be neither depressed nor rheumatic. Notice that neither nor and either or, their two probabilities sum to the total probability of 1 because it represents, these possibilities represents the entire sample space. So that's 0.52 plus 0.48 gives us 1 or 100%. Now for question C. A randomly selected student, find the probability that a randomly selected patient is depressed given that he or she is rheumatic. Once we're finding the probability of one event given another, or one event if another condition holds, then this is called conditional probability. So here we're asked to find the probability that a patient is depressed given that they also suffer from rheumatism, given that they have rheumatism. So on the condition, in other words, on the condition that a person has rheumatism, the condition is what comes after the slash. On the condition that a person has rheumatism, what is the probability that they are depressed? In effect, that's what we're asked. So to calculate a conditional probability, it is the probability of D intersect R. It's always going to be the probability of the intersection of the two events divided by the probability of the event that comes after the slash. That is the event, that is the conditional event. So we're going to divide by the probability of R. So always the event that comes after the slash, which is the conditional event, goes into the denominator when you're calculating conditional probability. So what do you look out for when you're faced with a conditional probability problem? You must look out for keywords like given that, or if, or on the condition that, or any synonymous terminologies. So we are given D intersect R in the question. Note that D intersect R is the same as R intersect D. The intersection can be expressed interchangeably like that. So we're going to put 0.06 here, which is the numerator. That's the probability of D intersect R, divided by the probability of R, and the probability of R, which is the probability that a person suffers from rheumatism, is 0.35. So here we divide 0.06 by 0.35 to get our result. So 0.06 divided by 0.35 is going to give us 0.17. So this is going to be 0.17, or roughly 17%. This is 17%. So there's a 17% chance that a person is depressed given that he or she suffers from rheumatism. So that's how we compute conditional probability. Now let's determine, based on question D, whether the two events are independent of each other. When two events are independent of each other, the occurrence of one does not affect the chance or likelihood of the other one taking place. So that's what we mean by statistical independence. Now there are a number of ways in which we can determine if statistical independence holds true, one of which is that the probability of D given R would be equal to the probability of the event before the slash, which is the probability of D. So if the probability of D given R is equal to the probability of D, or for that matter, if the probability of, let's write this the other way, R given D is equal to the probability of R, that is the event before the slash, then this is a condition for independence as well. Another way in which we could check independence is to see if, when we multiply the probability, so I'm going to write this out here, when we multiply the probability of the two events by each other, so that is, if I multiply the probability of R by the probability of D, and it works out to be the value of the intersection of R and D, then if this condition holds true, then we have also established that the two events are independent of each other. So these are additional conditions for independence. Additional conditions for independence. So let us see if the two sides here are equal. So two events are independent if the probability of D given R is equal to the probability of D. We worked out D given R earlier to be 0.17. And let us check the probability of D itself, which is the probability that a person is depressed, is 0.19. They are different. So what we realize is that in this case, 0.7 is not 0.17 is not equal to 0.19, and so we conclude that the events are not independent of each other. So therefore, the events are not statistically independent. Based on this information, are not statistically independent, which would really be another way of saying that they are dependent on each other. The two conditions that the patients are suffering of has some dependency relationship statistically. That's what this result would be suggesting. Let us now look at E, which asks, if the two events are mutually exclusive, find the probability that a patient either has rheumatism or suffers from depression. So if two events are mutually mutually exclusive rather, so if two events are mutually exclusive, one very important condition to know is that the probability of the intersection is going to be equal to 0. Because if two events are mutually exclusive, then they cannot occur together. So there's no intersection. So the probability of the intersection would be 0 if the two events are mutually exclusive. So this is a crucial condition for mutual exclusivity. The probability of D intersect R, or the probability of the intersection of the events which are independent, is equal to 0. Therefore, since we're asked to find the probability that a patient is either rheumatic or has depression, then we know we have to apply the general probability rule again, but with one fundamental difference, that the two events are assumed this time to be mutually exclusive, which means that we have to assume that the intersection carries a value of 0. The probability of the union of two events is always equal to this. The probability of one event, in this case D, plus the probability of the other event, which is R, take away the probability of D intersect R. To take away the probability of D intersect R. But since the two events are independent, we know that D intersect R here is going to be 0. So we really didn't need to include it in the formula. We could have just said the probability of D plus the probability of R, because we're asked to assume that the two events are mutually exclusive. We know that the probability of D from the question is 0.19. That's the probability that a person is depressed. We know that the probability that a person suffers from rheumatism is 0.35, and again the intersection is 0 because the two events are independent of each other. So this will give us an answer of 0.54 or 54%. So there's a 54% chance that a person will be rheumatic or depressed if the two events cannot occur together, if a person can't have both conditions together, which is what the mutually exclusive condition that we're asked to assume means. All right, let's continue now to another question illustrating the fundamental rules of probability. Keep in mind that total probability of all events in a sample space will always add to 1. The sample space refers to the list of all possible events in an experiment or from a particular situation. And probability values for any individual or joint event in a sample space has to be a value between 0 and 1. Cannot be negative, probability cannot be negative, and probability cannot be more than 1. So those are some important axioms to keep in mind when we are calculating probability. So here we are told that the probability that house sales will increase in 6 months, in the next 6 months, is estimated to be 0.25. The probability that interest rates on house loans will go up in the next period is estimated to be 0.74. And the probability that house sales or interest rates will go up in the next 6 months is 0.89. Calculate the probability that both house sales and interest rates will increase in the next 6 months. So the probability of both house sales and interest rates, we're going to use H for house sales and we're going to use I for interest rate. Feel free to use any symbol that you want to use. You could use HS and IR or A and B. It really doesn't matter. So what we're really asked to find in this question is the probability of H intersect, which intersect means and. All right, in the language of probability statistics, the intersection represents the joint occurrence of two events, that is, both events occurring together, which is what we are really asked to find here. So it's the probability of housing sales and interest rates increasing together. So we're really asked for the probability of the intersection here. So since we are told what the union is, which is 0.89, we're told what the probability of the union of the two events is. Remember that the union represents the probability. The probability of the union represents the probability of one event or another event. So we're told what that is. It says the probability that house sales or interest rates will go up is estimated to be 0.89. So that is in fact the probability of the union, 0.89, because the union is represented as the probability of one event or the other. And we also have individual probabilities for house sales increasing, which is 0.25, and interest rates increasing, which is 0.75. So we're going to use the general probability rule. We're going to manipulate the general probability rule to come up with the solutions. So the probability of A union B is going to be equal to, as indicated before, the probability of A plus the probability of B, take away the probability of A intersect B. So take away the probability of A intersect B. So this will be equal to the probability of A, well, let's use the actual symbols of H and I that we're using here. But as I indicated before, you can use A and B. It really doesn't matter. You just have to be consistent. So let's just use H. We identified H as house sales and I as interest rates. So H union I is going to be the probability of I plus the probability of H in any order. It really doesn't matter. It doesn't affect your answer. So it's probability, I'm going to state this as the probability of H plus the probability of I. Take away the probability of H and I. So take away the probability of H and I. So the probability of H, which is the probability that house sales will increase, is 0.25, as given in the question. And the probability that interest rates will increase is 0.74. And we're going to call H intersect I, which is what we're asked to calculate in this question. We're going to call that X, the unknown. However, keep in mind that we know the probability that house sales or interest rates will go up, which is 0.89. So we're just going to do some simple algebraic manipulation to find the value of X, which will give us the probability of H intersect I. So to condense this, we're going to simplify. 0.89 will be equal to, we're going to add 0.74 to 0.25, which is the probability of H plus the probability of I. And when we add 0.74 to 0.25, we get 0.99. And we're going to subtract X. Okay, now in order to make the negative X here positive, I'm going to bring it to the other side of the equation because it's easier to solve for unknowns when they are positive. And then I'm going to bring the 0.89 to the other side of the equation. It's positive on the left side of the equation, so it's going to be negative when it goes on the other side of the equation. So this is 0.99 take away 0.89. All right, and that will give us 0.10 or 10%, which is saying that there's a 10% chance that both house sales and interest rates will increase over the next 6 months. So that takes care of that question. Now we're asked to calculate the probability that neither house sales nor interest rates will increase over the next 6 months. So the probability statement here that we're interested in is the probability of H union I all complement. So that's the complement of the union. So neither is always the complement of either. We know that the probability of H union I is 0.89, and we know that to find the probability of the complement of the union, it's 1 minus the probability of the union, as discussed in the previous question. So this is going to be 1 minus H union I, which is going to be 1 take away 0.10, and 1 take away 1 take away 0.89. 0.89 is the value of the union. So it's 1 take away 0.89, which is going to give us 0.11 or 11%. So this is 0.11 or 11%. So there's an 11% chance that neither house sales nor interest rates will increase over the next month. And this is really, really very instructive and applicable in practical business world. Now we're asked to determine if the increase in house sales and the increase in interest rates over the next 6 months are statistically independent. In the previous question, I stated some of the conditions for statistical independence. And one of the conditions that I stated, so the condition that you use to establish whether two events are statistically independent or not, will many times depend on the information that you are given in the problem, right? So many times it will depend on the information that you are given in the problem. So in this situation, we're going to use the probability of H intersect I. So if H and I are independent, then the probability of H intersect I would be equal to the probability of H multiplied by the probability of I. Be equal to the probability of H multiplied by the probability of I. Both sides of the equation will be equal if the events H and I are independent. We found earlier H intersect I to be 0.10. We know that the probability of H, as given to us in the question, the probability that housing sales will increase is 0.25. What we want to establish is whether the right-hand side of the equation will equate to the left-hand side here. So this is another way of mathematically establishing whether two events are independent of each other. And the probability that interest rates will go up was given to us in the question as 0.74. So we're going to have 0.74 here. So is the left-hand side equal to the right-hand side? Let's see. So we're going to have 0.10. And then we're going to multiply 0.25 by 0.74. So 0.25 multiplied by 0.74. And what we get there is approximately 0.19. So what this tells us is that the right-hand side is not equal to the left-hand side. And because the right-hand side of the equation here, which is the intersection of the two events, is not equal to the product of the two events, that is multiplying the two individual events by each other, we conclude, therefore, that the two events, so therefore the two events, which specifically are housing sales increasing and also interest rates increasing, so therefore the two events are not statistically independent. So the two events are not statistically independent. Two events are not statistically independent. And that is how we apply the basic rules of probability. I trust that you found this video to be extremely useful in establishing a core understanding of the basic tenets and rules that govern probability functions and probability situations in particular. Thank you for your time. Thank you for tuning into the Learning Curve. And remember to like, share, and subscribe. See you soon.